Okay, a very good day to everyone. I'm here to present the features of the regression functionality of the analysis toolpack of Microsoft Excel. And so I wanted to share with you the table of values that we have. So I hope you're seeing this on your screen. So we have two columns, one for uh, our independent variable X, which is also called the predictor variable, and another column for the values of Y, which is our dependent variable, or what is also called the response variable. So what this table says is that for the independent variable X value 2, the corresponding Y value is 11.7. For X equals 4, the corresponding Y value is 10.5, and so on and so forth. So what we can do is we want to be able to analyze this set of data via regression. And what we can do first is we can consider the scatter plot of this data set. And so what I do is I highlight this two columns, including the row for the names of the variables. And then I click insert. And then there are multiple tools that we can use here, but the one that is particularly useful for us is this icon, which is called the charts icon. And then here you can see, again, several choices. So what I do is I click the scatter plot for this set of values. And as you can see, the horizontal axis gives us the values for the X variable, and the values along the vertical axis would give you the values for the Y axis, or for the Y variable. Okay. So in particular, if you have the value X equals 2, the value is 11.7, and it is approximated by this point. When X is equal to 4, the value of the Y variable is 10.5, and it is located here. It is approximated by this point. So this actually is the scatter plot for our table of values between X and Y. Now, we can already picture the best fitting line, or the regression model, for our set of values in the table. Okay. So what we can do is we can click plus, and this actually gives us a handful of chart elements. But for us to be able to picture the regression model itself, or the best fitting line, we check the trend line, and it is given by the dashed line in our in our coordinate system. So the dashed line again is our regression line, or the best fitting line, so to speak. And as you can see, it approximates very well. The line actually approximates very well the relative positions of the points in our scatter plot. And so we can say that like early on, that there is a very good linear relationship between the variable X and Y. Okay. And how do we actually verify all of this mathematically? Well, mathematically, what we do is the following. So I'm going to set this aside. And it is now time to use the regression functionality of the data analysis toolpack of Microsoft Excel. And so what we do is we first click the data tab, and then on the far right side of the panel, there is the icon data analysis. So let me just repeat that again. Okay. Okay. Now, the data analysis will actually feature a multiple set of analysis tools that we can use. But in our particular example, what is important to us is this, the regression functionality. And so once we have highlighted this, we press OK. And then there's actually some entries already in the slots for the regression window. And I just would like to clear this up, okay, so that we can key in the values that we are given. Okay. So for the input y range slot, we highlight the column for the y variables, including the heading. Okay. And then for the slot of input x range, we highlight the uh, the values for the column of x, and automatically it will pop up in the regression window. Since our first row is actually indicated by their names, so we check labels to denote the fact that uh, in the result, the first row of our table of values is actually signified by the names of the variables. And then we also check the confidence level because later on we will have an interpretation of the coefficients of our linear regression model using confidence intervals. Then I click the output range to denote at what part of our worksheet the summary results will actually appear. And so if I click this slot here and I move over to our worksheet, I will specify the cell A8 as the upper left-hand corner of our summary output panel. And we are now ready for this. So let me clear that up. So I wanted the upper left-hand corner of my results panel to be A8. And so we are now ready. So after these are all specified, I click OK. And then here it is. Here is the summary output of the regression done by Excel. And the summary output has actually three parts. The first part being the regression statistics, the second part being the ANOVA part, or the analysis of variance part, okay? And the last part gives us an indication of how the regression model looks like by specifying the coefficients in the linear regression model. So we're now ready to discuss each of the parts. I wanted to copy the summary output plus the table of values that we have onto my whiteboard, and I have previously done that already. So as you can see here, I have reproduced the table of values along with the results of the regression analysis done by Excel. And we are now ready to look at the first part of the summary output, which is the regression statistics. So the regression statistics actually tell us about the level of linear relationship between the variable x and the variable y. The multiple r, which is given here, can be thought of as the absolute value. So the absolute value of the actual correlation, between x and y. Now, if you will recall, uh, the correlation between x and y could actually take on negative values, but the multiple r value as given by the regression analysis made by Excel will always be a non-negative value. So the multiple r here, so multiple r will always be a value that is greater than or equal to 0, but less than or equal to 1. And what happens is the multiple r value actually gives us the level of linear relationship between the variable x and the variable y. So in this case, in our particular example, the level of linear relationship is equal to around 99.4%, which is really good considering the fact that the multiple r has a maximum value of 100% and a minimum value of 0%. The r square value, on the other hand, is literally the square of the multiple r value. So it's just the square of the first item in the regression statistics. And so if you will try to verify this using your scientific calculator, if you square this value, what you get is exactly the value for r squared. Now, that said, the r squared value actually has another name, and it is called the coefficient of determination. Now, the coefficient of determination actually gives us an indication of the level of explanation given by the independent variable x on the level of variation that is happening in the values of the dependent variable y. So in this case, since the value of r squared here is 0.9878, then we say that so let me change the color of the ink. The variation within the y values, is explained by the x variable to the level of 98.87%. Okay, so this is actually a good value because, again, normally if the multiple r is large, then the r square value will also be large. And this basically tells us that any variation within the values of the dependent variable y can actually be accounted for by the introduction of the x variable, which is our independent variable. Okay, now going to the adjusted r square value. So what is it? Our adjusted r square value here is 0.983736809, and the adjusted r square value has the same purpose or function as the r square. It is also an indication of how much the x variable explains the variation within the y variables The only difference being the adjusted R square takes into account the presence of possible non-significant independent variables. So in this case, we will find out later rather, that the variable, our independent variable x, is a significant variable, and this is actually the reason why when the adjusted R square value was computed, it is not so far off from the actual R square value. So again, the adjusted R square serves the same purpose as the R square, but it takes into account the possibility of the presence of uh, non-significant independent variables. And the standard error indicated here can be thought of as um, some kind of average distance between the actual y values and the predicted y values as given by the regression model. Now, we will have an equation for our linear regression model a little later when we go to the third part of the summary output. But for now, the standard error uh, has a value of around 21%. And so this is actually a good value because it is um, very close to zero, or relatively close to zero. Okay, so now we go to the second part of the summary output, which is the ANOVA part, or the analysis of variance. So what does this part of the regression analysis actually say? So ANOVA again is just the analysis of variance. And by its inclusion of the word variance, we are looking at sum of squares of differences. Okay, now in the ANOVA part, there are basically two parts. The part for the regression, which you can see here as being in the first row. And there is also a part for the residual, or the errors, okay, which is seen in the second row. Okay. Now, there are several columns which you can see in this part of the regression analysis, namely the DF, which actually is short for degree of freedom. Now, the degree of freedom for the regression part is given by k minus 1, where k is the number of variables present in our model. In this case, the variables are x and y, and so the value of k is equal to 2. So to find the degree of freedom, or the DF, for regression, so you carry out the subtraction 2 minus 1, or equal to 1. For the residual part, the degree of freedom is computed by carrying out the operation n minus k, where n is the number of pairs that we have in our table of values. In this case, n is equal to 5, and k is equal to 2 again, because we have only two variables. And so when we subtract k from n, we get the value 3. Okay, so the next column for the ANOVA part is the SS. For the regression part, this actually denotes SSR, or the sum of squares from the regression. And there is actually a formula for this. The formula is as follows. It is y sub I hat minus y bar squared, okay, where y sub I are the individual y values given by the model and the y bar that you see here is just the mean of the given y values. All right, so this is the sum of squares for the regression part of the ANOVA. And then we have the residual sum of squares, or SSE, which is given by the summation of uh, y sub I minus y sub I hat, okay, which again, the y sub I hat here is just the corresponding y values as predicted by our regression model. So this is y sub I, okay. All right, and the y sub i's that you see here are the actual y values. So knowing this, we now go to the column for the ANOVA, which is indicated by MS. Now, MS is simply the mean square for each part of the ANOVA. So let me clear up this space here. Okay. Let me correct this. So this is okay. All right. So we now go to MS. So just like in each part, MSR is obtained by considering the ratio SSR over, in this case, the DF of the regression part of the ANOVA. And so SSR in this case is given, for the regression, is given by 10.609, and then the DF is just k minus 1, or since k is equal to 2, so we have 2 minus 1, and this just gives us the value 10.609, which is actually this value here. Okay, so this is the mean sum of square, or the average sum of square for the regression part of the ANOVA. Now, just as there is an MSR for the regression part, there is also a corresponding average for the sum of squares, which is called MSE. And naturally, it will be formed by the ratio of SSE and the corresponding degree of freedom for the residual part of the ANOVA. In this case, SSE is given by 0.131, as you can see here. And this is divided by the degree of freedom for SSE, which in this case is equal to 5 minus 2. 5 minus 2. So n is equal to 5 and k is equal to 2. And so when you try to carry out the operation, you have 0.131 over 3, and this is just equal to 0.043667, which you can see in the second panel of the summary output. Okay, and the next column for the ANOVA part is the F column. So the F statistic is actually formed by considering the ratio MSR over MSE. So this is how the F statistic is defined whenever we use the ANOVA uh, functionality or the ANOVA part of the regression test or regression analysis. And so in this case, this is just equal to 10.609 divided by 0.043667. And this should give us 242.9542. Now, the basic assumption here, which is normally not mentioned anymore, is the fact that the level of significance here for the test is normally 95%, or rather 5% significant test. Okay, so it's basically 100% minus 95%. So level of significance of 5%. And what we mean by this is the following. So let's try to illustrate that graphically. So the F distribution actually is a curve that looks like this. Okay. And what happens is if we assign a level of significance that is 5%, okay, then it means that the far right end of our F distribution, okay, will have a region of rejection. Okay, so this is the region of rejection. So region of rejection. Which has an area of 0.05. Okay. So this is the area of rejection. So this part of the F distribution should have an area of 0.05. And as you can see, since the level of significance or the significance value for this particular F statistic is this much, this means that basically when you try to plot the F statistic that we have obtained, in this case, which is 242.9542, so this is 242.9542, then the area to the right of this number, which is indicated by this region here in purple color, is 0.000573.834. Okay. If we have a level of significance, actually what we're doing is we are implementing some kind of test here. Okay. And in particular, what we are doing is we are trying to implement the test where our null hypothesis of the slope of our linear regression model is equal to 0, while the alternative hypothesis is that our beta is not equal to 0. Now recall that if beta 1 is equal to 0, this basically means the assumption of no linear relationship. So there is no linear relationship between the x and y variable. Now, if there is some kind of linear relationship between the two variables, then we will have to reject the null hypothesis and accept the alternative hypothesis, where we are saying that the slope of our regression model is not equal to 0, and there is some kind of linear relationship between the two variables. So there is linear relationship. So in this case, the p-value is very much less than the assigned level of significance. So since 0.000573834 is less than the 5% or the 0.05, so we reject the null hypothesis, where it is stated as beta 1 is equal to 0, and we accept the alternative hypothesis, which suggests that there is some kind of linear relationship between x and y. And so that is for the second part of the regression analysis, or the summary output. So we now go to the last part of our summary output. So let me just okay. Let me just erase some of the items here. Okay, for the last part of our summary output, what we are given is again a table of values. So a table of values, okay, where you have two rows. First, you have a row for the intercept, and the second row is a row for the coefficient of the variable x in our regression model. Now, the first column for this part gives us the column called coefficients. And from here, we can actually form our regression model. So our regression model should be y hat, meaning it is an approximation of the actual line that best fits our scatter plot. So y hat is equal to b1 x plus b0, okay, where b1 in this case will be the coefficient coming from the second row corresponding to the x row. So this one, okay, and it is equal to negative 0.515 x, and then our constant is indicated here as 12.59. Okay, so this is actually our regression model. Okay, so our regression model is given by this, and the other columns that are included here are also quite important. It is quite important to bear in mind that when you are considering each row here in the third part of the ANOVA, then what you're actually doing is you are doing hypothesis testing. So for the first row corresponding to the intercept, the null hypothesis is actually beta naught is equal to 0, while the alternative hypothesis is beta naught is not equal to 0. Okay, and so in this case, the p-value, which you can see from this column, for the intercept is 1.16 times 10 to the negative fifth. Okay, so we have 1.16 times 10 to the negative fifth. And this is very much less than, again, the standard assigned value for the level of significance, which is 5%. Or in real values, or in real terms, it is 0.05. So what we do is we reject the null hypothesis and accept the alternative. And so from here, what we do is we are saying that the coefficient of our constant in our regression model is actually not equal to 0. Now, it's quite interesting to note that we could also do the testing by obtaining the t-statistic for this part of the summary output. So if you will notice, the standard error given by this particular row in this part of the summary output is this. Okay. So what will happen is we can actually determine the value of the t-statistic by the following formula, which is as follows. So beta naught minus beta 0 over the standard error. Under the assumption of the null hypothesis, our beta naught is equal to 0, and our B0 is what was computed here. So it's actually 12.59 minus the beta naught under the assumption of the null hypothesis is beta naught is equal to 0, and the standard error is, as shown here, 0.219165082, and this gives us 57.44528. Okay, and so if you will try to illustrate this using the t-distribution, what this means is the following. So you have the t-distribution. It is centered at 0 in this case. And then on both sides of the t-distribution, you have these regions of rejection. Okay, so the area here is 0.025, and then the area here is 0.025. Okay, now since the p-value is actually this much, okay, so it means that basically what happens is we got a value for t which is very much on this side of the t-distribution. So this is our value of the t-statistic. Okay, this is 57.44528. Okay, and this area here to the right of this particular t-value is 0.0000116, which is basically this. Okay. And so this particular t-value exists in the rejection region of uh, rejection region of our test, and so we reject the null hypothesis. Okay, so we reject the null hypothesis and accept the fact that the beta naught is not equal to 0, and which actually tells us that there is a linear relationship between x and y variables. All right, so we're almost complete in our analysis. Okay. Except for the fact that if we want to consider the rho for the x variable, okay, which here is given as, which is named the x rho, then what we have is, again, we are actually doing a test where the null hypothesis says that beta 1 is not equal to 0. Okay. So beta 1 is just a sum of our regression model. And the alternative hypothesis is beta 1 is not equal to 0. And what is happening here is we compute for the t statistic, which in this case is given by beta 1 minus, or b1 minus beta 1 all over the standard error. And under the hypothesis of the null hypothesis, our beta 1 is equal to 0, and the value for b1 is given by this, negative 0.515. Negative 0.515 minus 0 all over the standard error that you see here, which is 0.033040379, which in this case, when you carry out the operation, will just give us negative 15.587. And this is exactly the value that we see here. Okay. And because of this, okay, we can actually have a graphical interpretation of this, just like the one we did in the intercept for our regression model. So it's going to be like this. So it's going to be the t distribution. Again, it is centered at 0. Okay, and the fact that our significance level is equal to 5% or 0.05 means that these two regions here are the rejection regions, and each of these regions will have an area of, each of them will have an area of 0.025. Now, the t statistic that we obtained is negative, so it's on the left side of the distribution. And what this basically says is that the figure, or the value that we obtained, which is negative 15.587, is here in this side of the curve, and the area to the left of this number is given by this p-value, which is 0.000574. And so since this number exists on the left part of the rejection region, then we again reject the null hypothesis. So reject. And we accept the alternative, which says that beta 1 is not equal to 0, which actually implies a linear relationship between x and y. X and y. Okay. Now, finally, we can focus a little bit on the confidence interval. So the confidence interval, so the CI for the intercept in this case is given by the interval with left endpoint, in this case 11.89 to 2 decimal places, and the right endpoint as 13.29, again rounded off to 2 decimal places. And if you will notice, this interval does not contain 0, which is actually what the null hypothesis says when we were testing for the intercept. And so this is actually a confirmation that the value that we got for the constant in our regression model is significant. So coefficient value is significant. Okay. And the same thing could be said for the slope of our regression model, which is, okay, let's try to indicate that. So sorry for the distractions. Okay, so CI for x is given by the interval with left endpoint negative 0.62, rounded up to 2 decimal places, and an upper endpoint of negative 0.41. Again, estimated or approximated to 2 decimal places. And this means that since, again, it does not contain 0, it means that basically the value that we got for the coefficient of the regression model, the slope of our regression model, means that the value that we obtained is actually significant. So it does not contain 0. So slope of negative 0.515 is significant. And again, this brings us to the conclusion that the slope of our regression model is not equal to 0, and hence there is indeed a linear relationship between the independent variable x and the dependent variable y. And this can be seen by looking at the R square value of our regression model, as well as the multiple R value for our regression analysis. And so that's it. Thank you very much for listening, and I'll see you soon.